Good afternoon.
Good afternoon, sir.
So let's review a little bit of last time's talk. We started discussing about field programmable analog array, what is abbreviated as FPAA. Excuse me. Now, we know that the basic building blocks for FPAA are CAB. CAB stands for Configurable Analog Block, then input output, and some switching networks. Now, switching networks are responsible for communicating among the CABs, and there are also switches which make the interconnections within the CABs. Okay, so there are two types of communication. One is intra-CAB, another is inter-CAB. Now, what are intra-CAB? Anybody can say what is intra-CAB communication? What is the communication within the CABs?
Sir, the routing networks.
The routing for what? I am saying that intra-CAB and inter-CAB. What is intra-CAB?
Sir, intra-CAB is the communication between the circuit of a single CAB.
Within CAB, I am just showing.
Within CAB, yes. And inter-CAB is connection between two CABs and
just
more.
look at this. This is the basic building block for the switched capacitor circuit. Listen. So these are the basically the CABs. Now CABs consist of what? Operational amplifier and switches and capacitors. So here phi 1, if you just look at the diagram for the switched capacitor, so these phi 1 switches are there, phi 1, phi 2, etc. So these switches will make the connectivity within the switched capacitor. Okay, so that is intra-CAB connections. Is all right?
Yes, sir.
And when we talk about where is yes. Okay, and when we talk about the connectivity between the CABs, then these are called inter-switching. So there are two types of switches. One type of switches are outside the CABs, and another type of switches are within the CABs. So there are three major building blocks: inputs and outputs, CABs, and routers or switches. Now, apart from that, there are some oscillator circuits for clock generators and etc. So these are there. Then voltage references in the voltage control oscillator, those will be there. These are the minor portions. So this is the structure of FPAA. CABs, in between you will find the interfacing switches, and output sides. The signals are brought to the output world through the operational amplifier, and input analog signals will be coming through the input ports. So this is the basic structure. And these are the switches, okay, crossover switches. They are connected in vertical and horizontal. So by activating the switches, a particular CAB can be connected to another CABs. Most of the commercially available FPAs are structured like that, horizontal and vertical. Okay. So like here, if I just look at this diagram, 4x4 CABs. So the complexity when we buy the FPAA, the functional complexity depends on how many CABs are altogether there. So more will be the CABs, more will be the complexity, and it will be easier to implement the complex analog circuits within a single FPAA. And many FPAs connecting together can be made bigger and complex circuits. CAB implementations, last time also I said that discrete time switch capacitor design, that is the current topic we are going to discuss. Pulse-based design is still under research. It is not yet very much settled. But switched capacitor-based design, they are already in reality and the circuits are available in the market. And based on the switched capacitor, FPAA are commercially available. So basic advantages is a simple to design. They are flexible and they are much more accurate than using RC circuits. Here R resistance is totally replaced by switch capacitor circuits. And so the basic building blocks for FPA is the switches will be required, and switches are implemented by transistors, maybe P-type or N-type. And capacitors and operational amplifier. So these are the basic circuits. So here analog operational amplifier is the active component. Switches are also active component. So they're control switch made by transistors. And passive component is only the capacitor. So these are again the switches. Can view like that, local inputs. And these are the switches. Using the switch and by controlling the switch, you can make different kind of connectivity. And controlling the switch means controlling the gate signal. Okay, by giving 1 or 0, you can activate the transistor. Now there is a configuration memory within the FPA. Configuration memory, what is the task of the configuration memory? In fact, the configuration bit streams are stored in this memory. And this is a very fast memory and it's made of SRAM, static random access memory. So when we write the program in mixed signal processing language, typically a high level, okay, so is written in BSDL amps or Verilog amps. Then after compiling, we do the synthesis and then the bit stream after testing and verifications are downloaded onto configuration memory. So here, in fact, in the configuration memory, what information will be stored? Anybody can say? What are the information that need to be stored here? Say something, whatever you feel, you please, so that I can understand that you are getting the concept or not. Okay, what information you need? for making an analog circuit?
Sir, said that the device, the analog device, or
What,
said
what
the said input and the input and the output signal.
Okay, input output signals are already there, you can assume that. Okay, that information is fine. Apart from that, the most important information,
Sir, do we need the addresses, sir?
yeah, because since there are a number of CABs, each CAB will have an address, isn't?
Yes, sir.
Yes, sir.
Yeah, that information, but only address doesn't help. Which device will be connected to what device? That is most important, isn't?
Yes, sir.
When you just write a program for what? You just ask yourself, then only you will get the answer. These CABs are for what? For translating your analog circuits into the CABs. Is it not?
Yes, sir.
Yes,
No.
sir.
Each CAB is meant for what? Each CAB is meant for making the circuit, one circuit. For an example, I'm again coming back to the previous one. First, let's say this is, I don't know how you have learned to design an analog circuit, but I'm telling you my way of designing an analog circuit. Now, analog circuit design should be done based on the transfer function. For an example, even any system, whether it's analog or digital, a system should be defined. How a system is defined? A system is defined by transfer function. Now, transfer function, when we talk about, this is very important. I don't know, how you correlate the circuit. Circuit doesn't come all of a sudden. Whenever any designer, electronics engineer, wants to design a circuit, first question is, what is the circuit to be designed? Then the designer will be supplied with a transfer function. Now, what is the meaning of transfer function? Transfer function gives the total behavior of the system. These are output by input in time domain functions or in the discrete domain function. If it is continuous, then it's the Laplace transforms Hs, which gives the Laplace transforms of output by Laplace transforms of input. If it is in the discrete domain, very often we call digital circuits, then we define it by Hz equal to Yz by Xz. Now, getting these things, Ys by Xs or Yz by Xz, we find out what is the relations in Yt and Xt. Because if you take inverse Laplace, you will get Yt and Xt. Xt is the input and Yt is the output. Similarly, in the discrete domain, it will be Yn in terms of Xn and previous inputs Xn minus 1, Xn minus 2, etc. So that means in a continuous domain, we'll get a differential equations, output and input. For an example, you have a typical passive LCS circuit. LCS circuit, how the equation of the LCS circuit is governed? If the excitation voltage is Vt, then Vt equal to I into R, I is a function of t, plus L di dt, plus 1 by C integration of I dt. Now, once we get this equation, Then we know that R means register. We'll use a register. It's a series circuit because three things are added. Then we need an inductor and a capacitor, and we put the values accordingly. And if we want to implement it by discrete circuit, we need adder, subtractor or multiplier and delay units, and accordingly we put them and make the circuit. So that is the way of designing any circuit, be it analog or digital. Okay. So initially you will design your analog circuit depending on the need. It could be second order, third order, fourth order. That depends on the applications. Then you write a program corresponding to that. And after that, once you get the program, it will be compiled and it will generate the bit stream. So what information the bit stream will have? Because you are mapping your circuit, what you designed originally using analog, that will be translated to FPAA. So it will be requiring a number of CABs depending on the complexity. And within each CAB, whether it is RC circuit or CR circuit or RR circuit, it depends. And accordingly, the switches have to be activated. Depending on the value of the resistors, the timing T, capital T is related to the frequency. Okay. So all these things, all information has to be there in the configuration bit stream. And from there, accordingly, the connectivity will be established and a circuit will be formed. So now you understand why it is programmability.
Yes, sir. Yes, sir.
Depending on your need, the different parameters like value of the resistor. Value of the resistor is related to T. T is the time. Do you remember that? The resistance value is related to T, capital T. That is the period of the clock. So this information will be stored in the configuration bit stream. So it is a firmware. So if you want to change the circuitry, all that you have to do, you change your program, or keeping the same circuit, if the parameters need to be changed. What are the parameters? The value of the resistors, capacitors, etc. So just you change those. And to change the value of the resistors, all that you have to do, you have to change the clock frequency. And clock frequency can be changed by changing the counter value. Because clock frequency is what? Basic clock frequency divided by 2, divided by 3, divided by 4. So that is the programmable counter, what we discussed at the beginning. So that is the thing. Now, up to this point, do you have any questions? How FPAA functions? Please make it clear. Yes. Please.
No, sir.
Okay.
Understood, sir.
So now, so these are the building blocks already we have discussed. Switches. Now, AN23 1E04 is a commercially available FPA, and later versions are also available from NADG. NADG is a well-known company for analog circuit design. So this is the first one. What they announced is a dynamically reconfigurable analog device. Now I believe you understand now why they are called dynamically reconfigurable analog device. Because dynamically you can change by changing the contents of the bit stream of SRAM. I mean, same circuit, like the hardware is same, the platform, but just by changing the bit stream, the hardware is getting changed. It's becoming a different analog circuit. That means time to design is very less. Every time you don't have to design the hardware. So basic hardware you can design, and after designing, your game is with the software. By changing the software, your hardware can be used for different purpose. So the features, it consists of, I should not say 2 by 2 because now you will finding 4 by 4, 8 by 8. So n by n matrix of fully configurable analog blocks surrounded by programmable interconnect resources and analog input-output cells. So on-chip clock generator, that is there. Then lookup table is there, which enables waveform synthesis and several functions. Waveform can also be synthesis. Okay. In the lookup table, the sign functions can also be stored. And signal bandwidth, that is a low, 0 to 2 megahertz, but now advanced FPAs are available. The bandwidth has been increased. But this is the drawbacks of the FPAs. That's why still now they are not that popular as it should have been. So remember this thing, that FPAA doesn't mean that all the problems are solved. For low frequency applications, low frequency in the sense I'm telling you, low doesn't mean that some hertz and all. The signal bandwidth is in the megahertz range. Signal to noise ratio, that is also quite high in fact for FPAs. And your signal bandwidth, can you tell it's a function of which one? So far, whatever we have discussed from that, what is your perception? Okay, you ask yourself by asking yourself the simple questions. The speed of this RC circuit, the switch capacitor circuit, depends on what factor?
Time
the
constant, sir.
No. The clock period, isn't? How fast
Sir,
it is getting?
capital T.
The capacitor is,
Sir, the charging and discharging time of the capacitor may
that
be a
means what?
factor of.
Yeah, that means what? The T, capital T.
Yes, sir.
Yes, sir.
And so that's why the bandwidth is a function of that. And again,
Yes, sir.
So switching speed, that is the major bottleneck. So you have to get very fast switch. And then also the capacitor, like let's say switch is operating very fast, but your capacitor should have the ability to charge itself at that speed, is it not?
Yes, sir.
We know that Q equal to C into V. That is the basic formula. So charge accumulated is governed by what? Is related to the capacitance. And again, there is a limit to that value. So these are the most important thing. Now, I suggest one thing, when you will face the interview, always, any question, whatever the complexity of the question, you think yourself logically, you will immediately get the answer. Nothing is coming from the sky. Okay?
Sir.
Yes.
Hello, sir. Sir,
Yes.
what if the capacitors are pre-charged? So then the time will be.
No, pre-charge is how you will do pre-charge here. Here pre-charge is not applicable. Pre-charge means which is already charged. Okay.
Yes, sir.
Here you have to charge dynamically. For an example, let's come to the very first slide. You just look at this. Here, is there any question that the capacitor will be charged already?
No, sir. No, sir. No,
So
sir.
that's why these switches are there. These phi 1 switches. Can you see this? There
Yes,
are
sir.
two sets
Yes,
of
sir.
switches, phi 2 and phi 1. Why phi 1 switches? What are the role of the phi 1 switch?
So that the capacitor can get charged.
Charging.
No. Once you just look at this diagram. This is a clock. It should start getting charged from the positive end of the clock, phi 1
Yes,
or
sir.
phi 2. Or if I say phi 2, let's say this phi 2 isn't. Okay. So when phi 2 is on, there are two switches, phi 2 and two switches, phi 1. So when phi 2 is on, what should be the status of phi 1?
It should be off.
Off. So phi 2, when it will start? From this?
Yes, sir.
Okay. So when they are on, both phi 2 are on, then the capacitor will be charged.
Yes, sir.
And how fast it will be charged, that depends on what? Capacitance value is also important, isn't it?
Yes, sir. Yes, sir.
Yes, sir.
So now there's a limit to this value. That means this time, the switching time, there's a limit to it.
Yes, sir.
Okay. So that's why the speed of the switched capacitor is limited by this clock pulse. Again, the clock pulse, what should be the on period or period of phi 1 or phi 2? That also depends on the capacitor. For example, let's say phi 1 is high for a very small period, still capacitor is not charged. Then entire mathematics will be wrong.
Yes, sir.
So that means your capacitance value is also very important, isn't it?
Yes, sir. Yes, sir.
So that's why the bandwidth is limited by the clock frequency.
Yes, sir.
And here, in fact, still the work is going on how to make the bandwidth higher. That is the limitation. So this you should know what are the biggest limitations of the FPAA. Then we may ask the question, and if that is the limitation, then what is the need of using FPAA? Then forget about FPAA. Definitely not. In engineering, there's a word, very popular word, that is called optimization. Depending on the applications, we have to use the optimized design. The design which doesn't require very high frequency device, if we use that device, that will be over design, and you have to pay more for that. We have to design in such a fashion such that for a given applications, this offers the minimum cost. Okay. So what are the applications? That is very important. Maybe FPAA still as on date is not suitable for communication applications where we need very, very high speed. That's why for mobile handsets and all, you will find the DSPs are used. DSP processors are used. If you open your, like if your mobile handset goes bad, then open it, you will find a DSP processor is there inside. Okay. Nowhere you will find a PA. But there are some applications that we'll be discussing where APAs will be suitable. So its greatest limitation is on switching frequencies. and it will be requiring non-overlapping clocks. We have seen that one is 5-1 clock, another is the 5-2 clock, because when some switches will be on, some switches will be off, and vice versa. So you'll be requiring 2 phases clock. So these are some of the APS comparisons. So ZTEX track, this is 4 megahertz, and this is based on the bipolar technology. Now FPA applications. Analog signal processing, RFID to use. Because in the radio frequency range, we have that bandwidth for FPA. It's not a problem. Intelligent sensors, adaptive filtering and control, adaptive signal processing, front end. Front end, why you are saying adaptive DSP front end? What do we mean by that? In the front end, why do we require analog circuits?
Sir, because generally all the signals are analog in nature.
Yeah. But then why do you use FPA for that? Because
Sir, it will be
yes.
sir, it will be programmable.
No, programmable
If
is
we
okay.
need any change.
But why do we require some analog circuit? Already analog signal is coming. So then why you require? This is very important. Many of your ideas might be, if you get straight-away analog signal and use A to D converter, it will convert to digital. Then just give it to the digital signal processor, it will do that. No. These all are theoretical. In practical, the signal is contaminated with noise. Okay? So that noise needs to be removed before it should be processed for conversion. So that's why you need some analog circuit to filter out the noises and all from the signal. Okay, because raw signal, from the raw signal, the noises should be eliminated. That's why you need some kind of analog circuit. And here, the programmable analog circuit is better because depending on the need, the filter parameters might be changed. Okay. That's why.
Yes, sir.
Analog signals, then field programmable analog array, then you will get filtered analog signal, then A to D converter, and then digital signal processors. That's right. So there are many other applications. All these are most important is what I'm saying, deep neural networks. Now, why deep neural networks? Our intention of this lecture is ultimately to derive an architecture for neural networks and artificial intelligence. Now, in neural network, we don't require that kind of accuracy what we require for digital signal processing. For an example, I'm telling you. Say, in artificial intelligence, what we deal with, we try to mimic the human brain. We just take an example. Say, in front of you, there are 4 animals. One is dog, say cow, cat, and let's say buffalo. Easily looking at that, you will say, look, this is a cow, this is a dog, or this is a cat. Now, does it mean that throughout the world, there is only one shape of a cow or a dog? Like all the dogs look exactly same? Never.
No, sir.
Two dogs could be of totally different looking.
Yes, sir.
But they're dog, you understand. So that means you don't require 100% accuracy. But accuracy in the sense is a dog. In that sense is 100% accurate. But the features of, if you have 20 dogs in front of you, all 20 dogs will have different kinds of features altogether. Eyes could be slightly different, or colors could be different, many things. But they belong to the same class. Easily looking at that, you can understand, no, these are not cow. No, these are dogs. So that's why when you are just identifying a class, or you are selecting one element from a class, in the broader sense, you are trying to find out in which class it belongs to. But if we just compare with one thing, the feature of a person, you are trying to match. You got the image of a person and you are trying to match with a particular person. Then exact match is required, isn't it?
Yes, sir.
It's not that you are going to match whether it is a human being or not. You are going to match with the particular persons. For an example, in the airport, for this is an application of the criminal applications where a particular criminal is being searched, whether he is leaving the country or not. So in the immigration, there will be camera, real time. They are taking the snaps continuously. And from that, it is extracting all the features. Image consists of different features. And that feature will be compared with a feature in the known database. So here matching has to be perfect. Or let's say telebanking, but the voice is very important. Signature is a voice. And here the question of monetary transactions. And if the voice signature is not 100% accurate, it will be a disaster totally. The wrong person might get the money, the big loss for the bank. So here you need the accuracy. So that means two applications are different. When you are going for feature extractions or image classifications, pattern recognitions, there you need accuracy level should be very high. When you are extracting the image or you are doing the signal processing. But when you are trying to find out the class, which is important for your artificial intelligence and neural networks, there you don't need that level of accuracy. You need to check whether it belongs to this class or not. So there you can use some analog circuits. The reason why analog circuits? Because they are cost effective. They won't be that costly. They may not be of that high bandwidth, which is not required. But for communication applications, you need very high bandwidth. There you need the DSP, or let's say image transmission, or feature extraction. There you require sophisticated and high accurate computations. There you need to have digital signal processing. Okay, so these are the differences between analog and digital here, and as far as FPAA and FPGA are concerned. So the future of FPGAs, but still a lot of research work is going on. And I've seen some of the research papers where work is also going on to make it faster and faster. So SC designs will dominate the global market. It is expected that in future, because these are key to the success of mixed signal circuit design. That means one thing is very clear from our discussion, that we need analog as well as digital. The complexity of the analog circuits comparatively, switch capacitor based circuits, are not that complex like digital circuits. And for particular applications like neural network and artificial intelligence, they will be very much cost effective, whereas digitals are also required. So if we have some kind of chip where our analog circuits and digital circuits, that means kind of FPAA and FPGA in the same chip, that will be wonderful. So that is the work going on. So SC based analog memory. Now analog memories were not realizable until recently, but now 14-gate analog memory, that is also available now. It was in active research a couple of years back, but now it is available commercially. And enhancement of bandwidth, that is the, so major research in FPAs is the enhancement of bandwidth. In fact, I was going through a number of PhD theses in some US universities. I was finding that many of them are choosing FPAs as their research topic. In fact, I was talking with some of my friends at McGill University, and they have been working on bandwidth enhancement of FPAs. In fact, in 2005, Fabian Henrique, he worked with Joachim Becker to develop a maximum FPA bandwidth. And this collaboration resulted in the first manufactured FPA in 0.13 micrometer CMOS technology. So here, this robot dynamics, here also FPAs are used. It's found they'll be suitable. But in machine vision, still, the DSP processors, they are dominating the market. Means in the video processing, image processing, here high level of precision and accuracy which are required. Okay. And for neural networks, FPAs are used. So neural networks will go, when we will go for neural networks, we'll find that it need to perform huge number of concurrent operations of multiplications and addition in parallel. So in neural network, we can see that these algorithms exhibit large number of multiplications and additions, and which could be done in parallel. Just briefly, I'm giving you the computational structure of neural network. We'll discuss them when we'll go in details. So these are the structures of the deep neural network. So these networks consist of some input layer, output layer. Output layers could be a number of outputs. Here, even though we have shown only one, and a lot of hidden layers. In deep neural network, a large number of hidden layers are there. And these circles, what they do, they compute multiplications and addition. Okay, so these are the weights, in fact, these input lines. Okay, W1, W2, etc. So W1 is a corresponding weight. So Wi1 into I1 plus W2 into I2 plus 2. You know, these kind of computations have to be done. Anyway, the details of these things, when we the next sections, we'll be discussing this. So neural networks, they need to perform huge number of concurrent, it's a parallel operations of multiplications and additions. And since compared to fine level accuracy, speed is more important, because speed is important, not the accuracy here for neural network application. So exploiting inherent parallelisms for neural network computation is more desirable. So here, in fact, we can use the analog multiplier, because the reason being, analog multiplier, as far as the accuracy is concerned, is less accurate compared to digital multipliers. But complexity is much less. And they will offer the required speed. Cost will also be low. So that's why in neural network, analog multiplier, analog adders are becoming very popular. And that is the reason this analog circuitry is becoming popular along with the digital. So since digital is required, analog is also required, mixed signal is becoming the alternative. So analog multipliers are cost effective as they require less silicon. So up to this point, do you have any question?
No, sir.
So is it clear to you that why mixed signal processing?
Yes, sir.
Yes.
So this is a neuroclassifier. It's a long time back, about 30 years back it was. Now it is in a very mature stage. And that time it was 1.5 micron process and 0.6 watt power dissipation. It was very low, but now it has been developed further. You can, from the literature, you can get the so analog deep learning machine. The original contribution of this work was done by this Junjile University of Tennessee in doctoral thesis. So this work you can, from the net, you can get the research paper, on in the library you can get. A lot of, in fact, PhD works are going on analog circuitry, programmable analog circuitry for machine learning. But in brief, we can say that why deep learnings are very popular, why analog circuits are becoming popular, because of the reasons what I told. And in machine vision, basically it's an adaptive learning system. Analog design allows processing in real time, faster, extremely high degree of inherent parallelisms, scalable with current state-of-the-art fabrication technology. So in machine vision also, the analog circuits are coming, but still as on date, I would say the digitals are more popular. In robot dynamics, analog circuits are gaining attentions and mixed signal processing. So here, like analog and digital, both combination of both these circuits are giving the best results. So there is nothing like analog is the best or digital is the best. All depends on what is the applications and what for you are using. But still, one you should keep in your mind, but when very high speed is concerned, very high bandwidth is concerned, still digital don't have any substitute as on date. But as far as the RF circuitry, RF and all are concerned, they are analog. There is no replacement. So these are the universal issues. Precision, setup time versus execution time, storing results, error handling. You know that storing results means all the results are temporary results, are where the results will be stored, either temporarily or permanently. So for that you require the memory. And SRAMs are the best choice because SRAMs are very fast. Speed is much higher compared to any other memory. So configurable analog already we have discussed. So conclusion, which is important. CMOS technology is usually optimal for digital performance, while bipolar transistors are usually optimal for analog performance. Okay. This information is also very important. Okay. So can you tell why CMOS for digital circuits? What are the reasons?
Sir, static power consumption is very less.
Consume
Sir,
less area.
yes, sir. Packing density is higher, and sir,
And also, in fact, they offer very good speed, high speed.
yes, sir.
And bipolar transistors are usually optimal for analog performance. Okay. Until recently, it has been difficult to combine them in a circuit in a cost-effective manner. But now, in fact, because of the development of mixed signal processing, this both technology are put on a single semiconductor, like BiCMOS. I think I discussed BiCMOS when I was taking your VLSI class. Okay, BiCMOS is also becoming very popular.
Yes, sir.
And systematic design methodologies compared to digital design methods are more primitive in analog. That is true because digital circuits design is a very matured, whereas configurable analog circuits still is not that matured. So mixed signal circuits designing is still in the primitive stage. And digital circuit designs, lot of automated tools are available. Okay, like design automation tools. Analog also there are, but they are not that matured like digital. And overall, I can just share my experience. Analog design, it needs in fact more accurate knowledge. That's true. Because digital, I'm not saying that digital doesn't require knowledge. Everything, knowledge without that you cannot do. But my feeling is analog design is harder compared to digital design. Because in digital, you are dealing with only 0 and 1. Okay, but here many other things have to be considered for analog circuit design. And moreover, in analog circuits, what happens, the accuracy of the output, it depends on the physical values of the passive components like resistance, capacitances, etc. And it's very difficult to get exact value of resistors or capacitors. But in digital, once you get the values like you are dealing with zeros and ones. Just a minute, wait a bit. Okay. So this is about field programmable analog array, and these are the references. This paper is very good paper. Analog computing processing the way nature intended. And Paul Hassler discussed about some EDA tools. Now, if you have any questions on that, please. Otherwise, I will go to the next section. Yes. So,
Sir,
yes.
sir, I have a question regarding the power consumption of the circuits, because you told, sir, right now that these were very complex circuits. So how are we reducing the power consumption of these circuits, sir?
No, reducing the power consumption means, look, any FPA will have maximum power consumption that will be there in the manual, for an example. Okay. Out of that, depending on how much you are utilizing, for just a simple example I'm telling you, say you have 4x4, 16 CAVs, but your circuit complexity is such that you are using 12 of them, not entire 16. And your maximum power consumption, let's say something. So since you are using 12, the total power consumptions will be much less compared to if the maximum all the CAVs are utilized. So here
Yes,
the
sir.
power management circuits are there within the chip. These days, most of the VLSI devices, they have the power management circuitry. Now what the power management circuitry does, the portions which are not utilized, they're switched off. Even you must have noticed that in your laptop and all devices, any device, electronic device, whenever they are not in use, then your display and all these devices are off, isn't?
Yes, sir. Yes, sir. Yes, sir.
Similarly, in these FPAs and all, some automatic power management circuits are there. Always they are monitoring which parts are used. Okay. So, but there is a limit. For an example, let's say a particular chip. So it depends on the vendors. In their specifications, they will be mentioned that let's say this milliwatt of power is dissipated, and you are using all of them. So when the inter circuits are in use, then the maximum power dissipations will be that. If not, then it will be less than that. This is the thing.
Okay, sir.
And you just consult the manual, there it will be mentioned. For an example, if you just say this, here you will get this signal bandwidth is mentioned here. Signal to noise VCC 3.3 volts. So from the maximum current, that will be there in the manual. Here it is not there. You can find out what is the total power consumptions.
Okay, sir.
Okay. So in fact, so we have discussed in details about FPAA. Now we'll discuss in details about FPGA. FPGA basic principles we have discussed, but not in details for designing. Once this will be over, then we'll go for artificial intelligence. Okay, introductions to that and the architecture of mixed signal processor architecture, what we designed here. Now, if you have any questions, please. And another topic also I will try to cover, that is memory design, analog and digital. That is floating gate memory. I think floating gate, have you studied floating gate transistors?
Yes, sir. You have taught
Yes,
us
sir.
in the class.
No, okay, I taught in the class, isn't?
Yes, sir.
Okay.
Yes, sir.
So that will be required, that knowledge will be required. The floating gate memories, especially for analog domain, they are becoming very popular. But since we are talking about the analog circuits, analog computations, then automatically analog memory will also be required very much. Okay. And here you don't have any subjects on analog signal processing, is it?
Yes, sir. We do not have that, sir.
That is also becoming very popular now. Analog signal processing. Anyway, slowly we'll go. So next day I will discuss about FPGA in details, the design, hardware design of FPGA. Okay. Then we'll start this artificial intelligence and then architecture. Or AI, I think you have done the subject AI, isn't here?
Sir, only the embedded students have done it, sir.
Okay. Okay, then I'll discuss in details. Okay, so that's all for today. And if you have any question, please feel free to ask me.
Sir, I have actually a request, sir. Sir, the request is regarding, sir, if you can take some very few classes on extra classes or extra sessions on power management circuits or intelligence sensor. So that would have been very helpful if it is possible. It is a request.
Power management can be done, but on intelligent sensor, I have not done much work, truly speaking, So I don't think that I will be a very competent person, because when I talk about lecture, I believe in that level of discussing, not just for for the sake of delivering talks. Okay.
Okay, sir. Then, sir, power management circuits will be very helpful, sir.
Power management can be later on. I can discuss once everything will be finished. Then we can discuss on power management circuits. That's it. Okay.
Thank you, sir.
And another thing I can suggest you that since I'm discussing about mixed signal processing, analog circuits, analog signal processing is also very important. And today, the analog circuit design, the concept has totally been changed. Especially I've seen in US universities, North American universities, their style of teaching is a bit different. Because designing of a circuit is not from intuition. Like everything has to be given, and the description has to be given by the transfer function. And to understand these things, I think the mathematics, knowledge of mathematics is very important, especially Laplace transforms, Fourier transforms, Z transforms, differential equations. These things should be in the lip. If that is in the lip, then what happens, whatever the complex circuitry is given to you, it won't be any complex for you. Just you just state the problem, convert the problem into mathematics. Okay, and mathematics, then whole complex mathematics, you divide into blocks of like small differential functions. For an example, like a d2x dt square plus b dx dt plus cx, etc. And these things will be replaced by your devices. Now, what are the devices? If you see the entire differential world equation, in the mathematical world, you will find if you have differentiator or integrator, adder, subtractor, you can make any equations. Now, differentiator, if you have inductor, you can make a differential like d2x dt square. Equivalent is L di dt, dt cube dt square. Or integrator will be done by capacitance. Look, this mathematics and physics, they are interrelated. Why capacitor is integrator? Then you have to go into the basic function of the capacitor. What it does, it accumulates the charge. Accumulation is nothing but integrations, continuous. That's why its mathematical relation is governed by that. Rate of change of flux. And that is related to di dt. That means dt cube dt square. And linear relations with the resistors. So that's why easily any complex analog circuits can be formed by the differential equations. And these things can be done easily by switched capacitor circuits. You can translate it. And design the circuits. That is the whole concept. Okay, so even if you want some question answer session, whole session, we can discuss these things in more details. Okay. Any questions?
No, sir. No, sir.
Okay. Thank you very much. So next will be on Friday, I think. Okay.
Okay, sir. Thank you, sir.
Thank you, sir.